energy when we're talking about temperature. But you'll do fine. We're not going to worry about Part 9, Unit 1, probably this semester. So I reserve the right to bring it back if I want to. So that means that frees us up. So we'll finish up Unit 1 today. And like I said, we're going to, before your Unit 1 exam is on Tuesday. It's going to be across the hall in 502. So I'll have a little sign in case we forget. All semester, your unit exams will be on Tuesdays across the hall in 502. But what I promised was then we would begin Unit, 502. But what I promised was we would begin Unit 2 material. And so that's what we're going to do on Monday. So anyway, so temperature, what do you think? I have a few videos to see if this, oh, it's not working. Maybe the batteries. Temperature may not be what you think it is. When we think of temperature, we think of heat. And as it turns out, heat is energy, and temperature is only one thing to say how much thermal energy or heat something has. So what temperature does do, and I have a picture to kind of try to show you this, and it makes sense what my video does, my little animation does, is if we have two boxes, and this is, I can't remember how it does in animation, but if we say hot and cold, okay, if I were to show, and we'll make them gas particles, so if I were to show these gas particles, which one are the particles moving fastest? The hot one, yeah. And one of the ways we can do with showing movement is just show like an arrow. So I'll show a big arrow there, a small arrow here. And all this is saying is if I were to open a channel between the two boxes, okay, or let them come in contact, what's going to happen is these hot ones are going to migrate over here. They're going to bump. There's literally going to be collisions between those hot ones, and they're going to transfer some of their thermal energy to the colder ones. So when they do that, what happens to the colder ones? They go faster or slower? They go faster. What happens to the fast ones? They slow down. So that's kind of all that says. Spontaneous means it happens, just happens. Okay, we do know if you have a temperature of two, in this case, sets of gases, we do know that thermal energy will be transferred from the more kinetic energy to the one that was. Yeah, there's definitely an intersection between physics and actually there's something called physical chemistry that kind of deals with some of this stuff too. So heat. All right. So again, heat is a type of energy. So heat is a type of energy. Well, it's thermal energy. Okay. Yep. Heat is equal to thermal energy. So here's the deal. In order to know, and again, we're going to skip part 9, the next part. So I'll kind of show you how thermal energy works. If I have a bathtub full of water, here's my bathtub. And if I have a cup full of water, here's my cup. Okay, and they're both at, let's see, what's a good temperature to take a bath at? I don't know, would be 100 degrees Celsius. Let's go with metric Celsius. Maybe 78 degrees Celsius. Okay, so they're both of these sets of particles, these are water particles, have the same amount of kinetic energy. They're all running around at 78 degrees Celsius. But here's the deal. Which one has more thermal energy? The body of water in my cup or the body of water in my bathtub? How many people think the bathtub has more thermal energy? Me too. It has more energy because it has more mass. There are 3 things to see how much thermal energy or heat an object has. Those 3 things are the temperature, the mass, and the other thing you need to know is something called specific heat. And specific heat actually is specific for a substance. You have to look this up. So my point is that thermal energy is different than temperature. They're both great, but they're different. So we sometimes use heat and temperature interchangeably, but you're not supposed to. So here's the little animation I was telling you about. Yeah, the ice cubes have an extra thing in that we have a phase change. So if it's going from a solid to a liquid, actually before it, let's see, how does this work? It's weird. We kind of think of it stepwise. We kind of think of the cold ice cube. Let's assume it's at like -10 Celsius. We kind of assume that it kind of heats up to 0 Celsius and then actually uses some thermal energy from the hot water to go ahead and go from a solid to a liquid to break those intermolecular bonds. So if you have a phase change, it makes it a little more complicated than kind of no phase change. But there is definitely some of that going on. Yep. So we talked about intensive and extensive. We talked about chemical and physical properties, intensive and extensive. And you guys told me I think intensive is independent of amount. So if I go back here to my cup and my bathtub, okay, these are all both great bodies of water, small body water, big body water. They are at 78 degrees Celsius. It's independent of amount. Where heat is extensive. So extensive depends upon amount. And we said this has more heat, but has the same temperature, less heat. Okay, so. And I already kind of, the next part that we're not going to do, we talk more about this idea of thermal energy, the 3 things that you need to identify how much thermal energy an object has. I said you need to knock out its temperature, its mass, and something specific to it we call specific heat. As it turns out, water has a really high specific heat. Specific heat is kind of like how much energy, thermal energy it can store. And specific heat is also how much energy do you have to pump it up to make it change its temperature. Specific heat. And kind of like we saw, we've talked about what temperature does is to tell you the direction that thermal energy will flow. And it will always go from hot to cold. Thermal energy. So now we need to talk a little bit about temperature scales. These are the 2 temperature scales that if you're looking at weather.com, it says, what do you want to go with? And of course, the English is the Fahrenheit scale, okay? And the metric is the Celsius scale. So Fahrenheit or Celsius. So if you're like me, if I want to know the weather outside, I'm down with Fahrenheit. The whole Celsius, I get all confused. But Fahrenheit. One thing we have going, our English temperature system of Fahrenheit is we've got a lot more little niches. We've got a lot more degrees, a lot more options than the Celsius scale. You can kind of see that if you look at water and some kind of key stones with regard to water. We say that water will freeze or transition, freeze or melt, same thing, 32, and water will evaporate or condense, I guess, at 212. So you kind of count the number of, there's 180 units between these 2. Versus on the Celsius scale, they have more coarse units. So looking at water freezes at 0 Celsius and it boils or condenses at 100 degrees Celsius. This is under normal atmospheric pressures because actually the boiling point temperature is a little bit of a moving target. So 180 units versus 100 units. I'm going to talk about kind of 4 scales, 4 different types of scales. And as it turns out, the most sophisticated temperature scale is coming up, and actually that's the Kelvin temperature scale, is the most sophisticated temperature scale. As it turns out, Fahrenheit and Celsius are what we call, they're not ratio. You can't use factor label to convert back and forth between them. So they're not ratio level, but they're interval level. And I'll try to kind of show you the difference in scale. So this isn't just temperature. This could be a scale for length, a scale for time, a scale for anything you measure. So yeah, they're pretty good. Fahrenheit and Celsius are pretty good, but Kelvin is the best. It's ratio level. So what do I mean by measuring things and having different levels of measurement? These are actually listed from least sophisticated to most sophisticated. So least sophisticated to most sophisticated. So here's one. This is where you're talking about a characteristic of something and there is like no number value. It's just nominal. So we could go, we have a certain number of people with brown hair, certain number of people with orange hair, okay? There shouldn't be any sort of who's better, brown hair or red hairs, okay? If there's no implied ranking. Non-numerical, no implied rankings. Then there's non-numerical, but we do imply a ranking. And I'm not saying you should. You know how they say blondes are the smartest people in the world? So we could go ahead and take something like hair color, and there's no numbers such as hair color. Go ahead and say blondes, brunettes, or redheads. And we could say, we can imply a ranking. Smart, pretty smart, not so smart. It's non-numeric and we imply a ranking. Now, I told you that the Fahrenheit and Celsius scale was this interval. It's interval, which is pretty cool. Finally, with interval, we get to numbers. Okay? Numeric data, but the problem between interval and ratio is interval has numbers, but there's no true zero. Case in point, what is 0 Celsius? Well, 0 Celsius is the temperature at which water transitions between a solid and a liquid, 0 Celsius. But is there a negative Celsius temperature? Yeah. So the 0 is just kind of a point on a continuum. Okay. So ratio is the coolest, no pun intended, where you actually have numbers. You can go ahead and rank things. And if you have 0 in that measurement, that means actually absence of that thing. In the case of the Kelvin temperature scale, if we're at 0 on the Kelvin temperature scale, we are absent thermal energy. We're absent temperature. T is 0. So T0, heat or thermal energy is 0. By the way, we talked about this the other day, and that actually, the 0 Kelvin has been approached, but never achieved as far as I can tell. So 0, like I said, absence of measured quantity. So we could say that, this is 12 inches, this is 6 inches, this is 3 inches, this is a half an inch, this is 0 inches. So 0 inches means 0. All matter has mass and occupies space, so you can't really be talking about 0 length in terms of an object, but I'm okay with that. If you have something, a measurement at this most sophisticated level of measurement, we can go ahead and do the method that we've been using with making an inequality and go ahead and take an equality and use it as conversion factor. We can use the factor label method with that quantity in working problems. So, if you stay in chemistry, one of the things that we're going to see actually in chemistry, especially, we end up using Kelvin units instead of Celsius or Fahrenheit in our factor label problems. Well, it depends. All right, so going back and forth between the two. So the way you read this is you plug in a Celsius quantity if you want to get Fahrenheit. That's how this works. So you can get Fahrenheit if you're given Celsius using this. If you have Fahrenheit and you want Celsius, you would use this. You would take your Fahrenheit temperature, subtract 32 units, divide by 1.8. That will give you Celsius. And we've been talking about rounding in here, and actually the 1.8 and the 32 are exact numbers. So no uncertainty brought by subtracting and dividing. And just to kind of point things out, where the 1.8 came from was something I mentioned a little bit ago, that with regard to just water, boiling, the freezing point temperature and the boiling point temperature, on the Fahrenheit scale, you're talking 180 units. On the Celsius scale, you're talking 100 units, and that's where the 1.8 came from. And the 32 offset kind of came from, again, the freezing point temperature of water. On the scale we use, Fahrenheit, you're talking 32. On the Celsius temperature scale, which actually is more akin to what we're going to use in science, there's an offset of 32 degrees. So, do you guys have this one in your notes? I'll let you guys go ahead and kind of play around with this. What would this look like? So I have the Celsius temperature. At least go ahead and set it up. That's Celsius temperature, and I'm trying to get to Fahrenheit. If you go into an ER, which hopefully you guys haven't had to be in ERs too many times for yourself or for someone else, it depends. But they actually have a chart there going back and forth between Celsius and Fahrenheit. Just because nurses need to be able to do that. The Google's great though. If you ever have to, you just say convert 25 Celsius to Fahrenheit, and boom, it'll say 77. So let's work another one. In this one, we have 98.6 Fahrenheit. That's body temperature. And we're going to go ahead and we're going to convert that to Celsius. So go ahead and kind of plug in. This is a good example to remind you to show all of your work. Even if you plug into the calculator right on your test and such, if you don't show what you plug into the calculator, then you're in trouble. So I went ahead and kind of fast forward. So you have a ratio. In the numerator of the ratio, you take your Fahrenheit temperature, 90.6, subtract 32 units, and divide by 1.8. And this one, I think I've told some of you guys, one of my least favorite sort of, how do I round, is like this one, when we have both subtraction and division. Remember, no uncertainty brought by the 1.8, no uncertainty brought by the 32. So we're just going to go ahead and go with 3 savings. So a few more things. Yeah, now I remember I pulled a graph. I pulled a figure. I moved it this morning. So you probably had this figure earlier. I have this figure in 2 places. It must be an important figure. So all it's doing is kind of showing you milestones with regard to the transition temperatures for water. Water freezes at 32 Fahrenheit, 0 Celsius. It boils at 212 Fahrenheit, 100 degrees Celsius. Okay. And then down here, I'm kind of showing you the third temperature scale is the Kelvin temperature scale. And as it turns out, the Kelvin is metric and the Celsius is metric. Fahrenheit is not metric. The cool thing is that, and I don't know the history, but when they set up these 2 temperature scales, they went ahead and 1 unit on the Celsius scale is equal to 1 unit on the Kelvin scale. So that makes our life a little easier. You're going to see here in a minute, if you want to, and we do actually in science, go back and forth between those 2 metric temperature scales. All you got to do is add or subtract the offset. And the offset is right here, 273.15. So that's all you're going to do, add or subtract that, depending on which one you're going to go back and forth between. But notice that Kelvin will never have a negative temperature. And 0 Kelvin is equal to negative 273.15. So true story, I went to that Athol Planetarium, Chicago. It's great to get on a train and don't have to do the traffic and everything. But anyway, they have a lot of great exhibits, including their planet exhibits. So you walk around and they have something about, they have kind of stations where you look at each planet. Each planet, one of the things that they gave was the surface temperature, which I'm all about that, right? But on the little diagram for each planet, they would say, they would say that what is the surface temperature of this planet relative to negative 300 degrees Celsius? I was like, what are you doing? Negative 300 degrees Celsius. I'm like, it's not happening because the lowest Celsius temperature we have tonight is 273. I don't know if anybody else gets mad like that, but I get mad. And I still have not messaged Neil deGrasse Tyson, but it's on my list of things to do. I took a picture of it, and I'm like, dude, can you fix this?
It's kind of like Safarian, I think it was in Indiana, but they had that poster for all the sea life, except there's like golden like trout and stuff that don't have in the ocean on it. So it's just some guy puts on pictures of fish.
It's like a learning environment, right? People are learning from the stuff, the wonderful stuff they put up, but let's get it right. Oh my gosh. Yeah, that's pretty bad. I don't know. Man, oh man. So just a little bit more about that ratio level, that most sophisticated level of measuring temperature, the Kelvin temperature scale. We call the Kelvin temperature scale the absolute temperature scale. I think referring to the absolute zero. 0 kelvins, kelvins is the lowest temperature you can get. And I think I've kind of already been talking about this, that at 0 Kelvin, you have no molecular motion. And that's a big, hairy deal, because one of the tenets of matter, we say that all matter has mass and occupies space. The other thing is we say that all matter has molecular motion. You know, if it's not a molecule, it has some sort of motion. There's like the vibrational, the rotational, the translational, but all matter has motion. She's like, all right, so matter doesn't have motion, so anyway. It's interesting. So it's kind of a small thing, but I try to kind of train myself, and you might want to too. When you're talking about temperature, if it's Fahrenheit and for Celsius, you use the word degrees. Degrees Fahrenheit, degrees Celsius. When you're talking about temperature in kelvins, it's actually units Kelvin. Okay? And that's actually related to the fact that Kelvin is a ratio and not interval. Written red must be important. So this is actually of the 4, I guess, conversions you're going to do between temperatures. This one's the most common conversion with regard to temperatures, because Celsius is metric and Kelvin is definitely metric. So it's offset by 273. And sometimes, honestly, I can never remember if I add or subtract. But if I get a negative Kelvin, I know I did it wrong. Okay? And if I remember well, two things. I guess I can remember 0 degrees Celsius is 273 Kelvin. Walk it down, and I got negative 273 Celsius equals 0 Kelvin. So I forgot. So if you're given the Celsius temperature and you want to get to Kelvin, you add 273.15 units. Depending upon how many digits are in your Celsius temperature, the 0.15 may or may not do anything for you. And if you're given the Kelvin temperature and you need to get that back to the Celsius temperature, you subtract 273.15 units. So yeah, those are that of the conversions we've done are most important. So there again is the same figure we're talking about. So go ahead and set this one up and I'll show you what the answer is. So in this case, we have a Celsius temperature, we want to go to Kelvin. So what would that mathematical statement look like? All right, so in the form of a question, how are we going to round this according to sig figs or decimals? Decimals. Very good. And how many decimals? Just one. Yep, you got it. It's tempting. You're like, well, my calculator says 298.35. But to do it right, since the number, there's uncertainty in this number, and you know what? That's a good question. I'm not sure. I think this might be exact. I have to double check. All right, so let's go the other direction. What if you were given the Kelvin temperature and wanted it Celsius? Go ahead and set that up. So we take 450. I remember somebody cared enough to put the decimal there, so the uncertainty actually begins in the ones place. So how do we get around this one? How many decimals? No decimals. Yeah. We didn't talk much about it, but if you actually have, if your uncertainty begins, the uncertainty here begins in the ones. If your uncertainty begins in the tens place, whoa, and actually you have to round to the tens place. Yep, no decimals. So it should look like this. Voila! Is that the last slide? Mm-hmm. Dun dun dun. So yeah, we're not going to worry about energy this semester, but we are on Monday going to go ahead and do Unit 2, start Unit 2 with elements and stuff. It should be fine. And on Tuesday, take your test, and hopefully we'll have no more snow days. Oh my gosh, I looked at the extended forecast though, and I think we're going to be okay this weekend, but like next week it's snow, 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 snow. Really? I guess we have a moist atmosphere and